Okay, so this is an example of the negative spillovers or externalities, but it takes a little further in the book. It's an interesting finding known as Braess's paradox. Um, I'll explain the paradox aspect of it and why it's interesting after we get through it. So the setup is really similar to what the book does with driving and commuting. I think the book was inspired by Braess's paradox, but didn't push it all the way to its limit. So let's imagine people have to travel from a starting point to an ending point. I'll just call it finish. And at the start, we're going to say there are two routes they can take. Right? There's maybe two different ways that you could conceivably go from start to finish, and people might fight over which one they think is faster. But let's model that. So one might go via intersection A, another might go via intersection B. So one of them goes from start to A, and from A to finish. One of them goes from start to B, and from B to finish. Sloppy map drawing there. Now, the roads that these are driving on have different capacities and take different amounts of time. Braess's paradox is set up with the following idea. So let's say that this stretch of road between start and B takes 30 minutes to drive, no matter what. It's never very congested. We never have to worry about it. It takes 30 minutes. And the same is true of the stretch of road from A to finish. Right. So those are little stretches of road. I guess they're not that little. It takes 30 minutes, but to drive on them takes 30 minutes. And you might think of that as either they're really big highways, so it doesn't matter how many people are on them, and it takes 30 minutes, or they're just never congested no matter what. I think it's probably better to think of them as like those are big expressways, 30 minutes of time no matter what. There's just never enough people that these things get crowded. But then we're going to have some road segments that do get crowded, that are maybe smaller, city streets or things like that, that depend on the number of people driving on them as to how long they will take. And the numbers here are not super realistic. They're really exaggerated. But let's look at the road between start and A as one of these roads. And the minutes are going to be N1 divided by 25, where N1 is the number of drivers taking that road. That's a little laughable. It says that if there's one driver, it will take, 1/25th of a minute. But it gets at our point where as the number of drivers on that segment of the road increases, the time it takes to drive from start to A also increases. There's congestion. That's where the negative externality or the negative spillover effect is going to come into play. From B to finish, time is just N2 over 25 minutes. So start to A and B to finish, the roads are basically identical, but it's not always going to be the case in every version of this that the same number of drivers take both of them. So N1 is the number of drivers on the segment start to A, and N2 is the number on the segment from B to finish. So let's say there are 1,000 drivers, and what they care about is who want shortest travel time possible. That's what they care about. Now, in the first version of this, the way I've drawn it right now, you can probably already see what's going to happen. 500 people are going to take start to A to finish, and 500 people are going to take start to B to finish. Everything is exactly equal between all of them. But the idea would be that in this version of it, we want the time on the start to A path, which is N1 over 25 plus 30. In equilibrium will be equal to the time on the start to B to finish path. Like those two paths will take the same amount of time. How do we know that's true in equilibrium? Well, because if one of them was faster, we wouldn't be in equilibrium. People would switch to the faster road. So in an equilibrium, they will both have to be equal. You can do some work with that. Stuff cancels out pretty quickly. You get N1 equals N2, And since n1 plus n2 equals 500 equals 1,000 total drivers, so 1,000 people have to get from point 1 to point from start to finish, then we have n1 equals 500, n2 equals 500. The time for all is 500 over 25 plus 30, or 50 minutes. Everybody is taking 50 minutes. Half of them are going start A finish, half of them are going start B finish. This is an equilibrium. If one of them switches, so if somebody going start A to finish switched to start B to finish, to go the route that start to B to finish, they would be increasing that time, and it would actually be, they would go from taking 50 minutes to taking like 50.05 minutes or something like that. So nobody has an incentive to switch. Braess's paradox introduces the following idea. What if we add a magical new road? What if we add a road that goes between A and B? And what if this road is the best road we can imagine? So you might think, a good road would have a lot of capacity, would never get clogged, and would be very quick. Let's take it to the extreme. Let's make it as quick as possible. 0 minutes. It's like a teleportation between A and B. What does that do? Okay. Well, now this introduces a few possible ways through this, pattern here. You can go start to A to finish like before. You can go start to B to finish like before. But you could also go start to A to B to finish, that one. Or you could go start to B to A to finish. In equilibrium, so it's not necessarily true that they will all have the exact same time, but what is true in equilibrium is that any road that has somebody on it will be tied, or it's either tied for or the unique fastest route. What we usually see in these is that there's like 2 or 3 options that are all equally fast. There might be one that takes longer and nobody takes that path, but you get this interesting sort of outcome. But let's go through it. And here's a slightly different way of thinking about it, which is that A and B are now, there's no difference between them. Since you can move between them at 0 minutes of time, then I don't care which way I go. I just care about how do I get to A or B fastest, right? So what that means is from start, we know start to B takes 30 minutes. So drivers will only take start to A until that time gets up to 30 minutes. At that point in time, no one else would ever take that route. What that works out to be is N1 is 750. So if we think about that, like 750 people are going to go up here. It will take them 30 minutes. The other 250 are going to go down here. It will take them 30 minutes. Everybody's happy because it takes 0 minutes to move between these, so it doesn't matter which one you went to. You can pop to A or B as you desire, basically at 0 cost. And nobody wants to switch. The drivers who are going down here and it's taking 30 minutes, if they went up here, that would be 751 people. That would take slightly more than 30 minutes. The driver on the margin here, I guess, might be indifferent. The 750th person is taking them 30 minutes. If they go start to B, it takes 30 minutes. They're indifferent, but certainly, if we were at 749, it would be faster to go start to A than start to B. So that tells us that N1 equals 750. But then the same thing holds true on the right-hand side of this. Since you can easily move between A and B at 0 minutes of cost, or 0 minutes of time is the cost here, all you're going to do is compare the 30 minutes from A to finish versus the N2 over 25 minutes from B to finish, and take whichever one is less, which will mean in equilibrium that this is true because this N2 equals 750. Right? Again, since you can just bounce back and forth between A and B, you'll go to whichever one's faster. And that will leave us by the same logic as we have 750 people, 750 drivers going here, 250 drivers going here. We're going to have 750 there, 250 moving there. Let me erase these interior diagrams. So now we know, you can model this in different ways, but probably what's happening is 750 people are going up here, or we know 750 people are going start to A, but only 250 people go A to finish. So probably 500 people are jolting down to B. They're joined by the 250 people who already went start to B to make the 750 who go B to finish. Play around with this and try this. What if one of the 750 people who's going between start and A went start to B? Would they be better off? What if somebody 750 people who's going B to finish went A to finish? Would they be better off? You'll find that nobody can improve over this situation. So now, what is the time, right? Like, how long is it taking? Well, this means N1 is 750, 750 divided by 25 is 30, so this is 30 mins. This is 30 min. Time for all with the connector road is 60 minutes. It's longer than it was before. This is the paradox here. We've added something that should, you would think, reduce congestion. We've built a road, in fact, the best possible road that moves between A and B. And I'll note that it doesn't have to be 0 minutes. So if you make it 1 minute, 2 minutes, 3 minutes, you still run into these problems. The math is just a little more complicated. But we built this magical road that takes 0 minutes to go on. And the result is that every single driver now experiences a 10-minute longer commute. And so what's happening? The paradox happening here is that basically this connector road allows for the possibility of increased spillovers. So at the start, 500 people went start to A. When I say at the start, I mean before we built the road. 500 people went each direction. That meant each driver was only causing a spillover, a negative spillover, a negative externality on 499 other drivers. The two sets of drivers never interacted with each other. That one driver made life worse for 499 people, but whatever. Now, 750 people are going in both directions. And it's because these little times, right, before 500 people were on each of the segments that can possibly be congested. 500 people were start to A, 500 people were B to finish. That meant that those segments themselves took 20 minutes. That attracts drivers. So now there's the possibility, instead of only being on one of those and being stuck in the 30-minute the other way, instead of, if you were a driver, let me erase some of these lines so that I'm not continually drawing the same lines. If you were somebody who used to go like this, well, you can look at and you can say, this 30 minutes from A to finish, I can swap that out for 0 plus down here. This was 20 when we started, when we immediately built the road. So a bunch of them do it, and they impose externalities, and they keep doing that until B to finish becomes a 30-minute ride, until it's equal to A to finish was. So they're imposing costs on more of the population. It basically increases the ability to get a faster ride at the cost of all the other drivers, or of most of the other drivers. And so from an individual perspective, if you started off, you're going here and it was taking you 50 minutes, you look and you go, if you're the only person who switches, when we build that road, if only one driver ever switched, and so it was still, 500 people going start to B to finish, 499 people going start to A to finish, and one smart person going start to A to B to finish, that one smart person would find their commute time was 40 minutes, and they'd really love that. The problem is everybody's smart. Everybody's got Waze on their phone or whatever. They'll find the shortest time possible. And then by doing that, they will all impose costs on each other, resulting in everybody being slower. This is really counterintuitive. Uh, like it seems weird, but it actually has been shown to happen that there are road networks where eliminating a road, reducing capacity, makes traffic flow faster. So Braess's paradox is actually, I think, it was due to a lot of stuff with electrical currents. Actually, originally it was used in electrical engineering, but the famous examples of roads, there are two big ones. One is the Embarcadero Freeway in San Francisco, which came down after an earthquake, and it was this big freeway that ran along the waterfront. People thought, well, after this freeway gets torn down, it's going to make traffic much, much worse. And it turns out it did not. Traffic actually got better. The other example of this is in Manhattan, Broadway, right? Broadway, a big, thoroughfare that runs sort of diagonally across the island, but is a really big, big trunk route. Recently, starting, I guess it was probably 10 years ago now, but they started closing bits of it during the summer and just blocking it off and having restaurants be out there and stuff like that. And when this was proposed, everybody said this is going to be, terrible. This is going to make traffic so much worse. You're taking away one of the main thoroughfares for cars, and it did not happen, right? It did not make things worse. The evidence is that traffic times didn't really change at all. So there is evidence that exists, and it's really interesting. And again, the fundamental thing here is like the road between A and B allows people to cause negative externalities for others at a higher rate than they could before, which, not good. So you can play around with different numbers, but I just wanted to show it. It's the same example from the book, but just drawn up a little bit more. That people, this is functionally a 1,000 driver prisoner's dilemma. People pursuing their own self-interest create a worse outcome for all, a non-Pareto optimal outcome.